In this talk, we have 4 parts in total for our attention-enhanced Citrinet. First is the motivation. We will briefly introduce the background knowledge of Citrinet, which is a pure convolution-based ASR model. The second is to introduce the Jasper block used in Citrinet and how we include multi-height self-attention mechanism into Citrinet. We give experiments and conclusion accordingly. Okay, the background of Citrinet. Citrinet is a pure convolution-based architecture for automatic speech recognition proposed by NVIDIA researchers last year. In this architecture, there are several parts. So wave input preprocessing, for example, to change the speech augmentation and other preprocessing techniques. And after that, we have prologue, block, mega block, 3 mega blocks, and epilogue block. So these 5 blocks are using 5 times 2 layers of convolutional network. So totally we have more than 200 convolution layers in this Citrinet. The decoder is a very simple linear projection from the encoder tensor output to the vocabulary size. And inside one block, we call it Jasper block. So we have a detailed architecture here, which includes 3 modules. The first is a convolution module, which includes a dipswise separable convolution network, a dipswise and a pointwise, followed by a batch normalization and dropout. The second module is a ICE module, which is a squeeze and exceed model, so that it tries to project the number of C channel to C divided by 8. So it's a squeeze process. And then we project back and use the sigmoid to put a weight into the original output of the convolution module. At the same time, the third part is the residual module, which includes a pointwise convolution, so that it can be added to the output of the production of IC module and the convolution module. So this is the equation of the right-hand side of this building block of Citrinet. So it has achieved state-of-the-art accuracy for ASR with this pure convolution architecture, but for some Asian languages, such as Japanese, we frequently need 1000 epochs so that it can converge. This means frequently it converges very slow. So the question and the motivation of this talk will include these 2 parts. So the first one is, can we reduce this more than 200 convolution layers to be least? Because inside the convolution module, there are actually 5 repeats of this network without any residual connection. So this makes the training of this 10 layers of convolution to be relatively slow. Another one is that can we use attention network into this pure Xian module so that we can also account for attention to capture the global information of the input wave. So based on these 2 motivations, we propose our attention-enhanced Citrinet architecture. So this is the update. So we totally have 5 updates. The first one is very simple. So inside one Jasper block, we actually use FFN followed by multi-head self-attention here. And also we use layer normalization before applying the FFN. So this is a pre-layer normalization architecture. The second change is that we use layer normalization instead of batch normalization after the dipswise separable convolutions. The third one is to replace ReLU with Swiss. So ReLU is actually performing not that good in this deep neural network for ASR. And the fourth one is that instead of repeat this big block 5 times, so we only repeat once, so that we can get rid of 80% of the convolution networks. And the final one, the fifth update, is that we use bidirectional transformer style decoder instead of the simple linear projection CDC decoder. And this is still a non-autoregressive architecture, so we will describe the details of this idea hereafter. Okay, we come to our experiment. Our experiment is based on an open source platform for ASR TTS and NLP in NVIDIA named NeMo. And we have updated code here with a bidirectional decoder together with NeMo. So the training includes a linear combination of 3 losses. The first one is the CTC loss. The second one is the left to right transformer decoder's output, which is using KL divergence loss. Third one is on the other direction, right to left decoding. So we use some hyperparameter 0.3 and 0.7 to put them together as a final loss function. We also use label smoothing with delta to be 0.1 to the output, so that to relatively improve the accuracy. So during inference, we use a combination of CTC beam search and attention rescoring. So we briefly talk about the training detail. So we have an encoder of the wave, and we have a linear projection from the 500, for example, 512 encoder dimension, hidden dimension to the vocabulary size, and then we compute the CTC loss. At the same time, we use the output tensor encoder and send it to the transformer decoder, so that it can actually give us 2 losses, KL divergence loss. We see a detailed example here. So for the left to right decoder, the input is the reference ABC, and the decoder's input, we put the start of sequence here, and then we use the decoder together with the memory as an assistant. We use cross attention here, and also we compare the reference with the output of the decoder using the KL divergence loss. So quite similar for right to left decoder, we actually revert the input sequence from ABC to CBA and insert start of sequence at the beginning. We actually predict the same thing, ABC with end of sequence. And also we compare these 2 sequences. This is a reference. This is a model output prediction, and compute the KL divergence loss. These 3 losses, CTC, 2, KL divergence loss, will be linearly combined together. And the inference is quite similar. So basically we have a wave input, we use the encoder, linear projection. So we have a unbiased output hypothesis by the CTC beam search. And the output, every hypothesis will be sent to the bidirectional decoder. This is a non-autoregressive decoder, since we only do the inference once. So we do not generate the output step by step, but we only give one shot output. So we have the two actually scores of two decoders, and then we reweight the score hypothesis ABC by the same hyperparameter. Yeah, ADC score, left-right score, and right-left score. Okay, we report our result using the CSG Japanese 500-hour ASR dataset. The first comparison is Citrinet with a channel size of 384 and our attention enhanced Citrinet with a similar channel size. So basically, in terms of both absolute and relative CER, we can improve significantly the Citrinet result. And also, since we removed 80% of the convolution layers in Citrinet, so for every epoch, the training time is only 80% of the Citrinet. So basically 4 minutes instead of 5 minutes now. So this is a direct comparison of the three test sets of CSG dataset. Another comparison is our attention enhanced Citrinet with conformer. So basically, they are quite similar. The major difference is that in the attention Citrinet, we also use the squeeze exit module together with bidirectional decoder. So the comparison shows that we still can relatively improve CER more than 5% to 10% of the three test sets. And in terms of model size, so our Citrinet attention enhanced Citrinet only has 40 million parameter, but for conformer we have 135 million parameter. And the training speed, so for one epoch, for training conformer we need 10 minutes using two DGX2 machines, but only we need 4 minutes for attention enhanced Citrinet. So it's only 40% of the training time if we set the epoch number to be the same. Enlarge the training set, putting together CSG with magic dataset. So totally we have 16 plus 500 to be 2100 hours. So putting this together, we see that we compared with conformer, we still have a relative of 20% improvement of character error rate. And also compared with Citrinet, we have more than 10% relative improvement of CER. And since we have 5 updates to the original Citrinet, we do a evaluation study on these updates. So this is a attention enhanced Citrinet here, and this is the baseline. So if without the bidirectional decoder, we actually has a significant worse result. So it means that the bidirectional decoder counts the most. So for other parts, without feed-forward network, using batch normalization instead of linear normalization, and using Swiss instead of ReLU, we can see that their contribution slightly drops. So basically, most important one is bidecoder, and then FFN, and then linear normalization, and finally Swiss active function. So we compare the convergence speed also. So we're putting them to be 200 epochs, comparing attention enhanced Citrinet and the original Citrinet. We can see that at all the epochs, so the orange color converges relatively quicker than the original Citrinet baseline. Okay, to conclude this talk, we have introduced the attention enhanced Citrinet, which has smaller CER with only 80% training time of Citrinet baseline and 40% training time and nearly 30% model size of conformal large. Our code is open source, so you are welcome to try our code. That's it. Thank you very much for your attention.